Hello everyone, my name is Evan Mills, and today I'm going to be talking about open channel flow, like you see in this river here, which is essentially flow that is open to the atmosphere. And particularly we're going to be looking at what happens when you change the roughness of the channel and the flow rate. And so my open channel here is just this basic plastic channel I was able to find at the hardware store, which has a relatively smooth surface, and that's what I'll be using to achieve this flow. And as you can see here, my experimental setup essentially consists of this channel suspended on top of a bucket with water coming from my bathtub. So I was able to find some literature about open channel flow, and particularly this diagram does a good job of illustrating what we can expect. And so what we will expect, and you have to keep in mind that in this experiment we're going to be looking at the top-down velocity profile. And from this diagram, that would imply that we'll have a velocity that's the highest in the center and decreases as we go to the top and the bottom of the channel. So now we'll get into the first few trials here. And so this is just kind of what the setup looks like with water flowing. And you can see those black marks, which are really just for measurement. So they are each 1 centimeter long. So this first trial is using the low flow rate. And you can see once we drop that dye in there, we get that shape that we expected, which is kind of that reverse C curved shape. And then here with the high flow rate, we get what looks to be pretty much the exact same shape. So here's the schematic that I've set up, which essentially shows the origin where we'll begin taking our data points, as well as each of our axes and other information like flow rates. So this is what the setup in Tracker looks like. And essentially I've tracked it at these 5 different points along the Y, positive and negative Y of the channel, so that we can then use that data to construct a velocity profile in Excel. And so what you'll see here in the Excel graphs that are going to follow is the different names for each of these lines that I've tracked. So you'll see top, upline, center, downline, and bottom. So the data that you see in this graph here is a little bit complicated to think about, but essentially what it is I've taken the position and the time that Tracker reports, divided those to get a velocity so that we can get a velocity at each point. And then I've graphed that velocity versus time. And so what we would expect based on the literature that I found was that the center line would be the highest velocity, and then the further up or down you go, the lower the velocity gets. And as you can see here, that's exactly what happens. So that gray center line has the highest velocity, and then the next highest velocities is the up line and the down line, and then even lower you have the very top and the very bottom of the velocity profile. And so this lines up with our literature and what we expected. And for the high flow rate trial, you can see a very similar result. There's less data points here because I used the auto tracking software within Tracker just to see if it would give us the same results, and it does. And so we can see again that center line has the highest velocity and it decreases as you go up or down. In the next setup, I've added sandpaper to the channel to explore the effects that has. So this time we're using a red dye, just because it contrasts against the green sandpaper better. And you can see that we have a pretty similar effect here. We get the same shape, however, it becomes more turbulent and loses that shape more quickly, which most likely as a result of the sandpaper. And here's the setup I've constructed in Tracker, and it's essentially the exact same technique that we used for the previous flows. As you can see, the velocity versus time graph looks pretty similar to what we saw in the other examples, but do note that the velocity is quite a bit lower this time, whereas previously it was in the hundreds. So some of the drawbacks and deficiencies about this experiment, particularly with the way that I'm performing it, is repeatability. And so obviously flow from the bathtub is not super consistent. And in addition, we're not using purely laminar flow, which would be the most ideal way to test this. And along with that, some of the analysis here is simply visual, looking at the shape of the plug and saying that looks like what we expected. Ultimately, that's not the most scientific way to do it, but that's the best I could do. We were able to arrive at some pretty good conclusions, and we were able to graph the velocity profile for each of the scenarios and confirm that it matches about what we would expect from the literature. We also were able to compare the flow rates on the smooth channel, and we saw that there wasn't too much of a difference there in the profile. However, with the roughness, when we added sandpaper to the channel, we saw that the velocity was lowered quite significantly. That's all. Thank you very much for watching.